Hello and welcome to today's lesson on calculating definite integrals. So let's take a look at calculating definite integrals. So let's say we have the definite integral, and this is red, the integral from 2 to 4 of 12x squared dx. We will talk about what this means in a different lesson. Right now we're just concerned with calculating the definite integral. First thing we do is find the indefinite integral, the antiderivative. So taking the antiderivative of 12x squared, adding 1 to the exponent, dividing by the new exponent, this gives us 12 times 1/3 x cubed plus a constant. And then we're keeping track of our endpoints here with this new notation from 2 to 4. So now we have 4x cubed plus our constant going from 2 to 4. So the only thing new here between what we have done so far and our indefinite integral, or antiderivative, has been this notation where we're keeping track of those endpoints. Now what we're going to do is we're going to plug those endpoints into that antiderivative. So first we're going to plug in the top value, 4, and we plug that in for x. So I get 4 times x cubed, so that's 4 to the 3rd power, plus my constant, minus 4 times 2, that's my bottom number, 2 cubed plus my constant. So we plug in the top number and then subtract off what happens when I plug in my bottom number. So 4 to the 3rd power is 64. 64 times 4 is 256. And then 2 cubed is 8. 8 times 4 is 32. So now I have 256 plus my constant minus 32 minus my constant. And then the 256 minus 32 gives me 224. And notice what happens to these constants. Whoops. Notice the constants subtract off. Now this is going to happen every time we do a definite integral. And since this is going to happen every time we do a definite integral, effectively what's going to happen is we're no longer going to put this plus c in as long as we have endpoints. So when we calculate the definite integral from 2 to 4 of 12x squared dx, that gives us 224. Let's take a look at some more of these calculations. So let's say we want to calculate the definite integral from 0 to pi over 2 of cosine theta d theta. So finding my antiderivative cosine, that gives me the sine of theta, evaluating that from 0 to pi over 2, plugging in my pi over 2 and then subtracting what happens when I plug in 0. So I have the sine of pi over 2 minus the sine of 0. The sine of pi over 2 is 1, the sine of 0 is 0, and then 1 minus 0 gives me a 1. So the definite integral from 0 to pi over 2 of cosine theta d theta, that is 1. Let's take a look at another example. Let's say I want to find the definite integral of from 0 to 2 of x squared minus 4 dx. Again, we're going to take our antiderivative. So taking my antiderivative, adding 1 to the exponent, dividing by the new exponent, that gives me 1/3 x to the 3rd power minus 4 times x, going from 0 to 2. Plugging in my 2, I get 1/3 times 2 to the 3rd power minus 4 times 2, and then minus what happens when I plug in 0. So 1/3 times 0 cubed minus 4 times 0. So 2 cubed is 8. 1/3 times 8 is 8/3. Minus 4 times 2 is 8. And the second bracket, that's going to calculate to 0. So getting a common denominator, I have 8 over 3 minus 24 over 3, which gives me a negative 16 over 3. So the definite integral from 0 to 2 of x squared minus 4 dx is negative 16 over 3. Alright, let's do another example. So let's say I want to find the definite integral of sine of theta going from 0 to 2 pi. So the definite integral going from 0 to 2 pi of sine of theta d theta. The antiderivative of sine is negative cosine, and we're going from 0 to 2 pi. So plugging in 2 pi, this gives me negative cosine of 2 pi minus a negative cosine of 0, plugging in the bottom number. So that gives me a negative 1 minus a negative 1, which becomes negative 1 plus a positive 1, which gives me 0. So the definite integral from 0 to 2 pi of sine theta d theta, that gives me a result of 0. Now the reason why we can do definite integrals this way by using the antiderivative is due to the fundamental theorem of calculus. So let's take a look at sort of an explanation of the fundamental theorem of calculus. So if f of x is some function that has an antiderivative over an interval from a to b, that is capital F of x. So capital F of x is the antiderivative of little f of x. In other words, if we take the derivative of capital F of x, we get little f of x. Then the definite integral from a to b of little f of x dx is equal to the antiderivative when we plug in the top number minus the antiderivative when we plug in the bottom number. And this is why we are able to, this is what we've been using to calculate those definite integrals. Thank you for watching this lesson, and I hope to see you next time.